let me get you started with the hands-on by sort of explaining a bit of philosophy behind those two tools, and then I leave it to Oliver, Timo, and Julianus to walk you through it hands-on. OpenMS and top, there's always a bit of confusion. It's parallel. It's a software library, so you can write code using OpenMS, but it's also a collection of tools, what we call top, the OpenMS proteomics pipeline. And you have these Lego building blocks in the right-hand side of the slide. That's the fundamental idea. You know, Lego blocks are so fun because you can build so many different things out of them. So rather than having one tool where you have an interface and you click and it all works, with OpenMS you have lots of building blocks, and it's up to you to build something useful out of them or fun. So the idea is to have these fundamental building blocks for each analysis step. They all have more or less identical user interfaces. So once you know how one of these tools works, you know how the other works as well. And you put them together. These tools are designed in a way that there is no graphical user interface for each tool, but there's one application for visualizing mass spectra, that's top view. And you can run these building blocks out of these user interfaces. But you have small tools, and let me ask quickly, who has ever worked with Unix? Who has worked on a command line? Okay, then you know the Unix commands. You know that we have commands like cat or wc or awk, and you can just concatenate them into a pipeline. That's what the pipe symbol is for. So that's the idea. You have these small tools and you put them together in a meaningful way. So OpenMS 2 has 185 distinct tools. You're not going to use all of them in this course, but we will show you a sort of 24 that are really useful for your everyday work. They cover many different aspects, from extraction of information from files, file conversion, visualization, proteomics identification, and we're going to use the interface to database search and protein inference modules there, but there are also other things, retention time prediction, prototypicity prediction. Then there are tools for quantification, and we will use the label-free tools, but there are also iTrack and TMT and SciLec and don't know, MRM, SWOS, you name it. Odds are probably going to be 75% we got something for that. Then we have tools for metabolomics quantification, non-targeted, targeted, and also for metabolomics identification and various miscellanea. Each of these tools is rather short usually in scope, because we have the C++ library underneath, so the tools are a couple hundred lines in simple ways. Are all the data structures for dealing with mass spectra, and if you can write C++, then you can also learn how to write additional tools. But that's not what this course is about. I just want to show that so you've seen it. This is one thing you can do as well, not covered here. Instead, we will just use the existing tools. There are enough of them to cover most applications. And one of the key components of trying to put such a workflow together is actually interoperability. If you have different tools, then they usually don't want to talk to each other. It would be a very complicated world indeed. And that's where standardization is helpful. And we can do the same in mass spectrometry by defining not just like 5 standard diameters that everyone uses. We can also define standard file formats in order to ensure that what comes out of one tool actually is eaten up by the other tool. And these file formats are the file formats defined by the PSI, by the Proteomics Standards Initiative. That's a subgroup of the HUPO, of the Human Proteome Organization. And these guys meet regularly and define how should we store data for proteomics, metabolomics. And there are a couple of formats that you hopefully have heard of. MZML, that is how you store mass spectra. Make it very easy to use these formats because they want you to stick to their own software, to their own formats. But it can be converted. We will show you how that can be done. And the advantage is that these formats you can actually use without the instrument vendor software. And there are precedents where vendor formats could no longer be read after the company that produced the instruments went bankrupt, not in mass spectrometry, but related to that. And you can imagine what fun that is if you can't have access to your own data anymore. So we will show you how to convert the data. And there's also documentation for each of these tools. You can look that up on. For the tool, we basically have some text what it does. We have basically what we consider the man page for Unix tools. We have related tools, like this feature finder tool is often succeeded by feature linker, or is often preceded by a map aligner or peak picker. And this way you can also figure out what are possible tools that I need to know in order to use them. And there are also parameters in here. For example, this algorithm has a couple of parameters that depend on the instrument, and there are some values given. If you're working with QTOF or with an LTQ orbitrap, then these numbers are most likely suitable numbers for the tool. Installing OpenMS is relatively easy. You have these USB keys. I hope you tried it out already. And once you've got that running, then you can use it on the command line. And this here is just an illustration of how you can also work with these tools. We're not going to do that in this workshop, but just with Unix, you can use these tools like the tool file info. You say, I want to have info on this bsa.mzml that contains a BSA run. The tool just gives you some basic statistics, like it contains 500 mass spectra and 1110. And this type of information is kind of useful to have. You can quickly have a look in your tools, manipulate them. You can also dice them. For example, here we extract only the tandem spectra. And just with one call, we took bsa.mzml and wrote out the tandem spectra in a separate MZML file. So you can do all that on the command line. But we will use a graphical user interface for most of the course, and that is KNIME. It's a data mining tool that any of the Fortune 500 companies for internal reporting, but you can also do mass spectrometry with it, or genomics, because it doesn't care what data you analyze. It just gives you the framework to work with that. And it's kind of neat because it has also all these nice visualizations. So once you have the data in KNIME, you can do machine learning on top of it. You can use VK, you can use R. That's why it also is essential that if you go to the other courses and learn how to use R, you can just embed R. So if you change something in this visualization, you will see it also changing in the other plots. So it's a powerful analytics tool. It goes a lot beyond what you can do with Excel. And it goes beyond what you can do with R, because you can just embed R, you can embed Python, whatever your favorite language for that is. And we will give you at least a glimpse into the only tool that consists of two things, of tools and an order in which these tools are executed. In KNIME, that is what it looks like. You have these nodes here that are boxes, and you can drag and drop these lines between the boxes. Do I need that? I can also open the CSV file in Excel, select the lines, I don't care, and remove them. And that is true. But if you want the same workflow on 1500 files, then doing that and deleting the right rows without mistake in 1500 files, you will not manage that. I can guarantee it. So instead, you define a workflow that does what you want it to do. If you right-click, it has this configuration dialog. So you can specify which is the file that you want to process. You can specify which columns you want to remove, and you can just look at the dialogs and they tell you what parameters what. You can then also plot these tools. There is this icon here for reports that we will use, and we can also do that interactively. I show you very quick. But this is simple workflow that again read ratios for protein expression, and you can just change the plot in any way you like. This here is the intensity on the y-axis and the log ratio on the axis. So these are down-regulated, these are up-regulated proteins, and you can highlight them and mark them, highlight selected. And now in the table is automatically updated. It shows you the proteins that were down-regulated. And if you want to see which are up-regulated as well, you highlight them as well. And you will see that that then changes the table as well, so that the views are all connected. And it makes it convenient to navigate also complex data set and understand what's going on. If you want to embed then more advanced statistics or plotting capabilities that you learn, for example, in the R course, then there's a way as well. There's a node that's R snippet, and it takes the table from the left-hand side of the node. You write your code, and it outputs a table on the right-hand side of the node, and can be reasonably short. You can just have a function order that resorts the table. And you see in 3 lines you have put in your KNIME, your R code, or you can have more advanced scripts like this one that does normalization and box plots for quality control. We will discuss that later today. And it's a simple first proteomics workflow. That's an identification workflow that illustrates another concept, and that's automation looping. You know from programming languages that there's something like looping. We can do that as well. This workflow, for example, takes a whole set of files, like 1,500 files that you measured, each containing a proteomics data set. And zip loop start here defines start of this loop. So everything between this zip loop start and zip loop end is then executed for every file. And this way you can construct very complex, for example, search of these spectra against a database, compute the false discovery rate, discard the unreliable identification, and then merge it all back together into a complete result file. And we will learn how to do that in the hands-on section. All right, and I'll stop here and hand over to Timo, Oliver, and Julianus, who will guide you through this tutorial. And I'd like to point out that you should point up or shout whenever you need help. Everyone will be working at different speeds. We will try to answer all questions as they arise, but you know, there's many more of you than there is of us. So it might take a few seconds, a minute to get our attention so that we can help you work your way through the tutorial. Note that you don't have to work through every step of the tutorial. Some of you will work your way through that much faster and might look at other chapters as well. There's no pressure, just take the time to understand it. If you don't understand it, ask us and we will help you. All right, then let's get started. Everyone has their USB keys and handout.